Hi, this is a paper from the Computing Education Research Group at Brown University. Thanks for tuning in. Imagine you're asked to write a program to record traveler information. There are two main entities, flights and tickets. Each of these has some attributes. The flight has a number, an airline, and a departure time. The ticket has a number, the passenger's name, and their passport number. Now, let's think about how to represent this information in a program. Here is one possible organization. Our main data structure is a table of all the flights at an airport. One field in each row refers to a list of the tickets associated with that particular flight. But is this the only way we can organize it? Certainly not. Here's a rather different organization. We can have two distinct tables, one of flights and one of tickets. The flight number then becomes a key that we use to join information across the two tables. Is one of these better than the others? We're going to ask you to stop now, pause for a moment, and think about this. Done thinking? Hopefully you notice that there are trade-offs to these two designs. For instance, in the latter, it's typically more work to find just the passengers on a particular flight. However, suppose for a security reason you're given a passport number and need to find which flight that person is on. That's much more awkward to do in the former because the tickets are a secondary entity. These differences are the object of our study. Everyone who's built a large data-rich system knows that these decisions can have significant consequences for performance, security, maintainability, correctness, and so on. It's important to note that even though this is about the structuring of data, this is different from what the computing education literature calls data structures. That term seems to mean primarily internal decisions that are chosen on computational grounds. For instance, a binary search tree is a data structure, and you can balance it to speed up some operations. But a family tree represents an external genealogical truth, and you can't balance that. Data organization is all around us in computing, and its importance is only growing in our data-rich age. Despite that, it seems to barely feature in computing education research. It's time to change that. In this paper, we describe a pair of formative studies. In them, we give students pairs of data organizations like the ones we discussed earlier. Students are asked to describe the differences they see between the two and to indicate which one they prefer. Then we explicitly ask them to reflect on the pair as I show on the next slide. Finally, we ask them again for their preference to see whether anything has changed. We did these studies in two university courses. One was explicitly for non-majors, and in fact half the students were in high school. The other is an accelerated introduction to computing, consisting primarily of students with extensive high school computing experience. What is the reflection step? In the first course, students were prompted with very explicit questions which would surely have primed their thinking in very specific ways. For instance, the first question explicitly asks them to consider how they would find all underbooked flights. They don't have to write the program, just think about what such a program might look like. In the second accelerated course, students were just put in an IDE with the data definitions and asked to play with them. There's much more detail in the paper. Ultimately, we cared about three things. What, if any, facets do students notice initially? How does the reflection step affect them? And what is the impact of the different types of reflection? From 30,000 feet, here's what we found. Students mostly noticed issues with how one accesses data. Many fewer, but still a quarter, noticed issues with updating data, and with the prompts we saw earlier, everyone thought to mention updating issues. Numerous students talked about how easy or hard an organization would be for a programmer to work with. Very few talked about algorithmic issues. What may be a little surprising is that all these data are from the summer course, non-majors, and high school students. What may also be surprising is that the vastly more sophisticated students in the accelerated course did not do significantly better. Finally, After being made to reflect on the data, many students changed which organization they preferred. In short, there's a lot going on here. The paper goes into much more detail. What can we conclude from all this? First, we think this is a critical skill in our data centric world. Computing education needs to evolve to cover more of this. Unlike traditional data structures, data organization is accessible to students who have relatively little computing experience. In fact, students from diverse backgrounds may observe things that a more conventional student might miss because of their lived experiences. In short, this is also a kind of computational thinking. Data can enliven many computing courses, and thinking about modeling real-world scenarios lets us bring data into curricula from early on and have rich discussions around it. This work, and specifically our method, connects to many interesting theories in psychology. There's a lot more to explore there as we discuss in our related work. Finally, we have only scratched the surface. Notice that we didn't present any pedagogy at all, we just showed students things and saw what they said. Interestingly, they said a lot. But what would an explicit pedagogy centered around data organizations look like? Thank you for listening.